And we're back. Where did we leave off?
IR spectra covering that it looks at functional groups. Some about symmetry. I think that's where we kind of left off.
Yeah, so symmetry, basically, if your thing is symmetrical in a certain way, it gives you different hierarchies, more or less. And you can tell on Raman and you can tell on normal IR.
I said ramen, like the noodles.
No, you've never heard
No.
of specters?
No, I'm not.
All right.
He didn't take instrumental with us.
No, I heard that. Yeah, let's see. I might have to.
So, I can't explain Raman simply, so.
So. I'm trying to remember,
Ramen specialist tells us about polarizability.
right,
Just how polar like the functional group is,
what we could.
if it can be polarized.
Oh.
Mhm.
You know what that means? What does that mean?
Like it's more electromagnetic here, over there. Yeah.
Hey,
I learned that.
you're learning something.
Okay. So,
Alright, so
you guys
Raman,
bring up Raman spectra,
Raman.
and what's the context of why that's important in IR?
Oh. It's because.
Comparable tower.
Ramen is complementary.
Oh, this is complementary. Okay.
Glasses.
I do, and I have contacts in my eyes.
Do you want to clarify glasses?
Comparable IR spectrum and Raman spectrum, and can tell you a lot about a molecule.
Can the same piece of equipment do Raman and normal IR? Or the two separate things?
Thingamajiggies? All right, now we must refer to instruments as thingamajiggies.
Well, come
Exactly.
I call them machines. I call them machines, and he's like, it's not.
Ask him if we have a ramen machine.
Yeah,
Ramen machine.
and he's like, they're instruments, not machines. I'm like, but they got moving parts and stuff, so the machine is like, they're not. You don't get data from machines. Well, I thought I heard you guys talking about Boltzmann distributions at one point. What does that mean?
Boltzmann distributions tell you the populations of states, of energy states.
Okay, not like amount of people in like Illinois.
Well,
No.
you can't treat those that in all honesty.
I can treat it as people.
Well, because its populations are just kind of like the amount of
It's an
particles,
analogy.
Yeah.
amount of particles in a certain spot that can be excited.
Yeah,
Potentially be excited
know
for
how
energy.
energy states, if a molecule has a lot of energy, the Boltzmann distribution is higher. There's more distribution among energy states.
Higher.
There's higher energy states have more energy in them and more electrons.
That's how
Typically-
and how we can actually
Yeah.
explore the population of our states. Usually all the the molecules would be, or all the electrons would be in the ground state because at room temperature.
Yeah.
We don't have much energy, and yeah, it's pretty stable, being at ground state. So it's difficult to get to anything of a higher energy level, even though the spacing between the ground state versus energy state one, it's pretty big. It gets smaller as you go higher, but it's hard to breach that first energy state.
How do you go up with energy states?
Well, kind of like in IR, we get those we get the vibrational energy, but just with like, say you see a vibration that's like 2,200 wave numbers, that's just exciting to the first energy state. So it kind of gives you perspective of how hard it actually is to reach another energy level.
You can do that by like adding heat to something.
Yeah.
Add energy to a molecule and you'll activate more energy states.
Yeah.
Yeah.
Nice.
more heat.
Yeah.
Yeah, heats. Energy.
So you guys are talking about how bonds move back and forth, or like how molecules move back and forth.
Yeah.
So like, how does something not break then? So like, do bonds have strength?
Okay, we're going to ignore that question,
I'm
because
just-
you guys.
I'm just reading up the board.
No, he's trying to keep.
Bonds have
Yeah.
Yeah.
Cover everything.
I love it, like, did they just break, or did they have some strength? Well, I sure as hell hope they don't break.
Yes, they do have strength, and then when you add energy to it, those bonds move a lot, and then that's how you get IR.
So how does that show us kind of like a perfect parabola? Harmonic in a harmonicity oscillator would just show us a bond length and when it's stretched and compressed. So we kind of have like 0 at the center, negative. So when it's compressed, you'll have the left side, and when it's stretched, you'll have the right side. But then you can look at the Morse potential.
You show me a picture.
Yeah.
He doesn't know what it looks like,
Visual
so.
aids.
But then you have the Morse potential, which can actually tell us, it's a more realistic model where it actually can tell us where our bonds might actually break, and that's the limit that comes out at the end.
See, right here's where it's like this. Highest energy state, it's most stable, and right up here is the limit that Susan's talking about, where the bonds are. Like, held against each other.
So does like every bond have its own number of before it breaks then? Like every molecule have like each one has their own unique breaking point? Like it gets built up.
This based on like kind of like distance. He's saying that like based on what we're talking about with this. With the Morse potential, right? This graph, right?
Because we have an
Yeah.
equation for.
The Morse
Oh,
potential
so
comes-
you're talking about like the disassociation.
Yeah.
When it breaks.
So once it gets closer to this 0 point,
The flat line or the curve?
the flat line,
Flat line.
so once you can see it. Get closer to here,
Mhm.
that's dissociation. This is its breaking point.
Oh, okay. And does each one have its own breaking point? So like a bond between this and this is different than a bond between that and that?
It's based on the distance of, yeah, so as they get further from the way, they're more likely to just.
Okay.
As
So that can
when
also
it's-
tell us a lot about the molecule.
Noise.
What else we got? Any major insights?
Point in the middle of IR.
It's not allowed.
Nice.
Also,
Oh, that
suddenly you can read very well.
Well, that's because that's bigger, it's other
Bigger,
parts
it's a
small.
different color. And it's not all cramped, except why I didn't see the knot is because there's no space in between that. And so my eyes just read over every time I get.
So- You know about allowed transitions versus not allowed.
Remember hearing about them, I don't know the difference.
Okay.
Oh, no. How did I?
So allowed transitions are obviously ones that can be excited. Not allowed are ones that have to undergo a spin flip.
Mhm.
So they're not allowed because you can't actually go into them.
Or they don't follow rules,
They don't follow some rules.
there's a lot.
And so in the classical IR, there's this period, you'll have a bunch of peaks and then it kind of flatlines and then peaks again. And in that period, that tells us where there are not allowed transitions.
At the peak or at the bottom?
Space in the-
The space in
The
the
cube,
cube.
the cube zone,
So that's how you know if something's not allowed or where it's.
where it's less likely to be present,
Oh,
because you see a bunch of transitions, bunch of energy states going up, down, up, down.
Yeah.
And then, that's your empty zone,
Mhm.
and you have more transitional states.
I remember Keller talking, we had like this thing and then he's like, you know, this way, and then it can't go down this way because it's not allowed.
It's talking about the Jablonski diagram.
Yeah. Those things are fun.
So anything that turns to the
No,
right
I
causes
wouldn't.
a spin flip.
Sorry, was that Ulysses?
No, I'm saying anything that goes from singlet to triplet is
Not allowed.
not allowed.
What does that mean? What's singlet versus triplet?
Degeneracy.
Yeah.
You are.
Let's not insult our guest.
You makes it so easy.
I know it's Austin.
So degeneracy is, how to explain it?
It's for
It's just
orbital
repetitive
energy.
states.
they're like
Yeah,
the same
so the
thing.
energy
Of
blitz. Kind of?
The energy of different states being the same.
Yeah.
Yeah.
It's the same energy.
So you know how in electron filling, we've got those the different levels of essence, we've
Oh, yeah.
got 1 and a P, it's got like 3.
Yeah.
That would be the degeneracy we're talking about.
Like within the same letter, that would be,
Well,
just
within the
specifically
same
level.
energy level.
So let's just say that we have the energy level of like 500, and then we have the energy level of 1200. At 500, we have one energy location, one degeneracy. So there's only that amount of space in there I can actually use.
you don't want any degeneracy. Like Ellen DeGeneres.
And then,
No.
and then we go up there and we have three spot spaces, and that's basically three degenerate states.
There you go.
Okay.
That's a hard word to say.
Big words.
So remember how like, well, I don't know, I was, this PX, PY, PZ, those are all degenerate states.
Oh, okay. Interesting.
Alright, anything else? What else we got?
Why do we not see stuff in the liquid phase?
Think about it.
Liquid, I'm thinking of liquids.
Thinking of liquids?
Yeah, I'm thinking
Are you
about.
thinking about IR in liquids?
You like what?
I feel like it'd be a little loose.
Oh, ionic.
Definitely.
This would
take
be
out
a
of
little bit freer.
No.
Take them
Bonds
around.
will rotate.
Yeah.
Yeah.
So
Or
what interacts more, molecules in gas phases or liquid phases?
Which one moves the fastest?
I would say gas.
Why?
No, she said which one moves the fastest.
I don't know if
Gas.
it's right or not. I'm just
But I
saying.
Oh.
think, but if I had two liquids, I feel like they'd come together easier
They
than
interact.
gas. They're just kind of like.
Yeah, so with the gas phase, you can pretty much assume that the molecules are individualized and they all are doing their own thing and they're pretty far away from each other, so they don't interact at all.
Mhm.
So they're discrete and precise.
Yeah,
We can actually see the transitions and the excitations a lot easier. With gas stage rather than liquids, so that's what gives us more of like our like broader peaks. Say for like water, that OH peak.
Yeah, yeah. I was gonna say, like, I definitely have ran IR on liquids before, and
Oh,
I've
now
gotten
you have.
stuff. I mean, I will in the future. So like, why, like, I guess what that question says, why do we not see stuff like this in liquid phases? What is stuff referred to?
it's
As-
more of like specific peaks.
and pinpoint,
So it's easier to get, you'll get better IR if it's a solid compared to
If
a
it's-
liquid.
isolated.
It's a gas.
It's better if it's a gas.
It's in a liquid state, it's gonna react with the liquid around it, and you're gonna get less definition in actual seams.
So that's
Solid
is
state.
worse.
You better worry about your solid. Have all of it show up in IR, along with the change of. I'm just trying to take it out.
Alright,
It's
you got anything else?
really not.
I think that's it, I think that covers it. Do you
I've-
feel smarter now?
I've learned a lot. I don't think the word smarter would be beneficial to you.
You can
I hear the word quantum, so I'm gonna say I don't know, which is a right answer.
Yes.
There you go.
Alright,
Everything.
alright, one last thing,
What's your one last thing?
what can I tell you now?
IR.
Actually learned anything, or we're horrible teachers.
IR shows
It's
you,
either we don't.
IR shows you functional groups. It's better, if you do it in gas stages.
Nice,
Because of how close things are, and then you would have other things in that area that the IRV. The IRVs, the movements,
yeah,
bonds, like molecules, the bonds can break. And so there's like, you can do, see like when it's gonna break by Norman. Man, I think that's pretty much, you learn some new vocab words that I have to study at home.
You could also tell the difference between isomers.
Oh, yeah, isomers, yeah.
Isomers.
Symmetry.
Symmetry, there
Yeah,
we go.
symmetry, yeah. So I think the beneficial lesson here today.
I'm glad it's beneficial for you.
Yes, I feel more prepared to go into P-chem.
I'm glad we can add more brain cells.
Yay! Yeah, take it right now. We'll
Find the
pop
average.
it. Alright.
average.
We good to go?
Thank you for watching.
You should edit it so after Nikki hits the bag.
Hey, Lucy.
Oh, yeah, here you
Bye,
go.
guys.
Just like, here's it.
And the John.
Yeah.
Come on, Jeff.